Welcome to section 10.1, three-dimensional coordinate system. We're going to take a look at what a three-dimensional coordinate system looks like, and we're also going to look at some uses of it and some applications. Let's get started.
In this slide, we can kind of look at the difference between a x and y axis, our traditional Cartesian plane here, versus the three-dimensional. So our x-axis is kind of forward and backwards here. The y-axis will be more left and right, and our z-axis is going to be more of an up and down axis. So for positive values, we can see what we have in front of us: x moving forward, y moving to the right, and z moving up. If we had negative values, x would be moving back, y would go to the left, and z would then go down. Let's go ahead and try some examples for graphing three-dimensional points. Let's go ahead and start with the point 1, 4, and 5. Again, our first value here is x. Since it's a positive x, we're going to move to the right 1, we'll move out 1. Then we're going to move forward 4 for y. 1, 2, 3, 4. And now the hard thing to kind of visualize here is we're going to be moving up 5. So 1, 2, 3, 4, 5. And we're just going to kind of go up 1, 2, 3, 4, 5. And here's our point floating up in the air. If I take my point and I change it to now be negative 1, negative 4, and negative 5, we're going to be moving slightly differently. So instead of going out 1 for x, we're going to be going kind of back 1, so negative 1. And then we're going to be going to the left for y, so 1, 2, 3, 4. And now I have to go down. Again, this is kind of hard to visualize. We're going to be floating down 1, 2, 3, 4, 5. So it's going to be moving down 1, 2, 3, 4, 5. And there would be our point. The z-axis is always the most difficult, but you got to kind of visualize how you're moving up or you're moving down on our z-axis. If you don't get it right on, it's okay, as long as you kind of get the idea of moving left, right, and then up or down, depending on what our values are.
The distance for any 2 points, x1, y1, z1, and x2, y2, z2, is given by our distance formula, where the distance is equal to the square root of x2 minus x1 squared, plus y2 minus y1 squared, plus z2 minus z1 squared. So this is going to operate the same way our traditional distance formula would operate, except we have this third coordinate here, the z value, that we have to accommodate for. For our example here, we're going to find the distance between the points 419 and 216. We're going to go ahead and match up the right coordinates. So we're going to match up our x values, match up our y values, and our z values. And as we plug it into our equation, we see that we've done it. So I have 2 minus 4 squared, 1 minus 1 squared, and then 6 minus 9 squared. One thing to point out is I didn't identify which point was x1, y1, z1, and which one was x2, y2, and z2. And the fact that we're going to be squaring each one of our components means that the order doesn't exactly matter because we're guaranteed to get a positive quantity here. When I go ahead and simplify my information and add it together, I end up getting that my distance is equal to the square root of 13. Here we have another formula to help us find the midpoint between 2 points, x1, y1, z1, x2, y2, and z2. And that formula is going to be x1 plus x2 over 2, y1 plus y2 over 2, and then z1 plus z2 over 2. Very important to note here, we are adding our quantities together because we are averaging the value or the distance in between the 2 points. And then once you've done this, you've successfully found your midpoint. For our example here, we're going to find the midpoint between the points 5, negative 2, 3, and 0, 4, and 4. Again, notice we're going to be adding together our coordinates and then dividing by 2 so we can average that distance. When I go ahead and plug in my values into the formula, we have 5 plus 0 over 2, negative 2 plus 4 over 2, and then 3 plus 4 over 2. Again, I want to note that I haven't actually set up what values are x1, y1, and z1, because since we are adding them together, we're going to get the same value regardless of which direction we add. Once you simplify though, no matter which way you added them, again, we should get the same answer, which is 5 halves, 1, and 7 halves. And this is now the point that's in the middle of our two endpoints. One of the main reasons why we need to be able to find the midpoint and use our distance formula is for the equation of a sphere, which is our three-dimensional step up from a circle. We can see that our equation is for centers h, k, and j, and radius r, given by x minus h squared plus y minus k squared plus z minus j squared, where h, k, j again is your center, and then it's equal to r squared, which is your radius. Once again, this is just a step up from our circle equation because we're adding in our z components. Looking at an example here, we're given our center of 1, 2, 3. We know our radius is actually equal to 3. So I can go ahead and directly plug this information into my equation for my sphere to go ahead and find that. And we end up getting x minus 1 squared plus y minus 2 squared plus z minus 3 squared, and is equal to 9 because I squared my radius. And I'm not going to go ahead and square or simplify my expressions. I'm going to leave it exactly like this because when it's in this form, I can pick out my radius and also my center. For this example, we're going to find the equation of a sphere, given the information that we know the endpoints of our diameter, which is 2, negative 2, 2, and negative 1, 4, and 6. It's very important that these are the endpoints of our diameter because we can apply finding the midpoint, which would then help us give the center of our circle. So if I go ahead and apply my midpoint formula to my endpoints, then we have 2 minus 1 over 2, and then negative 2 plus 2 over 2, and 2 plus 6 over 2 to finish getting our exact center for our sphere. And we end up getting 1/2, 1, and 4. Now I can go ahead and try and find my radius. In order to find the distance of our radius, I know that the radius is half the length of my diameter. And since I already know the two endpoints for my diameter, I can go ahead and use them to find the distance between them and then cut that in half to find the radius. So I'm going to go ahead and plug in my points and simplify my distance. And I end up getting that my diameter is the square root of 61. So to take that and translate that into my radius, I'm going to cut that in half because once again, our radius is half of our diameter. And I end up getting that my radius is in fact radical 61 over 2. Another way I could have done this since we calculated the center of our sphere, in the last example, is I could have used that center with one of these endpoints to find my radius. Now that we have gone ahead and found our center and our radius, we can go ahead and plug those into our equation for our sphere and do some simplifying to finish getting our equation. So if I do that, I end up getting x minus 1/2 squared plus y minus 1 squared plus z minus 4 squared is equal to 61 over 4. One last step that we could do if we needed to is I could multiply both sides by 4. That way I would have equaling 61. You would have a 4 in front of each one of your components. It's not exactly necessary though, because again, in this form, I can pull out exactly the radius and the center for my circle. All right, for our last example here, we're going to try and find the equation of a sphere. Unfortunately, here we see we have a lot going on. I've got several x and y values and z values. So we're going to go through the process of completing the square, where we're going to complete the square for each one of our components. The first step is to go ahead and organize our information so we have our x's, y's, and z's together. So I have my x's together with x squared minus 2x, and then same thing with my y's, I combine them, and my z's, and I have grouped them together so I can go ahead and start the process of completing the square. Before we can do that, we want to verify that the coefficient of our square term is in fact 1. So I do have a 1x squared, a 1y squared, and a 1z squared. If that wasn't the case, I would factor that out of both of my terms to get that coefficient to be 1. All right, now that I've done that, I can go ahead and start completing the square, which is taking half of my middle term and squaring it and then adding it to that expression. So I'm going to do that for each one of my three components, for my x, my y, and my z. And that's how I got my 1, my 4, and then my 9. Again, we took half of a middle term and squared it and added it into each one of my components. Again, added half of 4 squared, which is 4, and then half of negative 6 squared, which is 9. On the other side, I have to add the same thing. So since I'm adding 1, I also added 1. Since I'm adding 4, I'm also adding 4. And lastly, since I added 9, I'm also going to add 9 to make sure my equation stays balanced. If again we had a value in front, let's say I had a 2 here, then this value would be an 18 because I have to multiply this 9 by that coefficient on the outside. So I'd be adding an 18 on the outside instead. Now that I have completed the square, I can go ahead and factor my expressions. All right, and remember that we're always going to factor as x plus half of our middle term, or y plus half of our middle term, and so on. So you can say I have x plus half of negative 2, which is 1. I have y plus half of 4, which is 2. And then z plus half of negative 6, which is 3. Now that we have the equation of our sphere, I can go ahead and use that equation to pull out my center and my radius. So I'm going to use these components for x, y, and z to pull out my center, and then use what the equation equals to find my r value for my radius. So we can see that our center then is going to be the point 1, negative 2, 3, and then our radius is going to be the square root of 6. All right, guys, that does it for our notes. Go ahead and get started on the homework, and good luck.